All right, let's dive into one of the greatest detective stories in the history of science, all to answer one single massive question. What is everything really made of?
I mean, think about it. The chair you're on, the screen you're looking at, the very air you're breathing, what is the fundamental stuff that makes it all up? The answer, it turns out, is something so ridiculously small it's totally invisible.
Now, you might think our story starts in some fancy, high-tech lab, but nope. We have to go way, way back to the minds of ancient philosophers.
And what's wild is that about 2,500 years ago, on opposite sides of the world with no way to talk to each other, brilliant thinkers in both India and Greece came up with the exact same incredible idea. Their thought experiment went something like this. Imagine you have a piece of gold. You cut it in half, you cut it in half again, and again, and again. Eventually, they reasoned, you'd hit a point where you just couldn't cut it anymore. You'd be left with the final, fundamental, uncuttable particle. They called it paramenu, or in Greek, atomos, which literally means indivisible. But for all its genius, it was still just that, an idea, a really good guess. There was zero proof. And the search for actual hard evidence? Well, that would have to wait for over 2,000 years for the birth of experimental science.
Okay, let's fast forward to the late 1700s. The game is changing. Scientists are finally starting to measure things with incredible precision, and in doing so, they start to stumble upon the first real clues in our mystery.
So the first huge clue, thanks to guys like Antoine Lavoisier, was this. In any chemical reaction, the total weight of the stuff you start with is exactly the same as the total weight of the stuff you end up with. Nothing just vanishes, and nothing appears out of thin air.
And you can see that principle right here. If you weigh your ingredients, mix them all up to cause a reaction, and then weigh the final result, the scale doesn't budge, not one bit. The matter just rearranged itself. It didn't go anywhere.
The next big piece of the puzzle came from Joseph Proust. He figured out that chemical compounds are like perfect recipes. They are always made of the same elements mixed together in the exact same proportions.
I mean, take water. It doesn't matter if you get it from an iceberg, a swamp, or you make it in a lab. By mass, it's always going to be 1 part hydrogen to 8 parts oxygen. Always. So, okay, these were the rules of the game, but nobody knew why these rules even existed. So who was the detective that finally cracked the case? Enter an English schoolteacher and chemist named John Dalton. Dalton, in the early 1800s, basically connected all the dots. He said, what if matter is made of tiny, unbreakable little balls, atoms? Well, if they just rearrange themselves, that perfectly explains why mass is always conserved. And if they combine in fixed ratios, say 2 hydrogen atoms for every 1 oxygen atom, that explains why water is always water. He took that ancient guess and turned it into a real scientific theory. And what's so cool is that Dalton didn't just have the idea, he visualized it. You can see his original symbols here. He created these unique little pictures for each element, a circle for oxygen, a dot for hydrogen. This was the very first attempt to create a visual language for chemistry, all built on this one core idea. A symbol represents a single atom.
Dalton's theory wasn't just an explanation. It was the start of a whole new way of describing the world. And to talk about atoms and how they hook up, well, chemistry needed a proper language.
So, over time, Dalton's little pictures got simplified into the 1 or 2 letter symbols we use today. You know, H for hydrogen. Sometimes they come from the English name, but other times, and this is pretty neat, they come from the old Latin names, like Fe for iron, from the word ferrum. So here's the crucial point. These symbols are like letters in an alphabet. And with this new, standardized alphabet, we can write the recipe, the chemical formula, for pretty much any compound that exists. And there's a really precise logic to it. The formula, like this one for calcium hydroxide, is basically a code. It tells us exactly how many of each type of atom are needed to perfectly balance each other out. So here, we need exactly 2 of those hydroxide groups for every 1 calcium atom to make a stable little package. Okay, so the theory is solid. We have a language for it, but one gigantic problem was still staring everyone in the face. If atoms are real, but they're impossibly tiny and light, how on earth do you count them?
Well, the solution was pure genius. Chemists decided they didn't have to count atoms 1 by 1. Instead, they invented a special counting number, just like we use the word dozen when we mean 12 of something.
And chemistry's special dozen is called the mole. A mole of anything,
Gold atoms, water molecules, whatever, is always the same, very specific, and very, very large number of particles.
And here it is, the magic number, 6.022 times 10 to the 23rd. It's called Avogadro's number, and it is just mind-bogglingly huge. I mean, that's not 600 trillion, it's 600 times billion trillion. That's how many particles are packed into one single mole.
But here is the real magic trick. The atomic mass of one single carbon atom is 12 atomic units. As it just so happens, a mole of carbon atoms weighs exactly 12 grams. You see, this brilliant idea creates a perfect bridge from the invisible world of atoms to our world of scales and beakers. We can literally count atoms just by weighing them.
So let's just recap our whole detective story. We started with a brilliant philosophical guess, thousands of years ago. Then, we found some serious clues hidden in the laws of chemistry. The case was finally cracked by Dalton's atomic theory, which then gave us a whole new language, and finally, a super clever way to count the uncountable with the mole.
So, the really important thing to take away from all this isn't just the history, but the incredible power this knowledge gives us. It's the foundation for everything from creating new medicines to designing new materials. It's how we change our world. Which, of course, leads to the final, big question. Now that we can actually count and control the building blocks of reality, what are we going to build next?